It's good to be here. As you can probably tell from my voice, I'm actually from the South, so if I start talking real slow, just kind of speed me up a little bit. But we'll try to accomplish a lot in a short period of time, talking about DOE 2016 and the impact. But first of all, let me get started. Kind of going back, I want to take a trip down memory lane a little bit, go back about 40 years. Who can tell me, who can recall gas at $1 a gallon? Can I get a show of hands? I got a few there. Okay, who can recall gas at 75 cents a gallon? I got a few. Ooh, the heads went down less. How about less than 50 cents a gallon? Yeah, okay, we got a few old guys here. Bob, I think you're one of them too. Okay. And this all started back in the 70s as part of the Energy Conservation Program set up by the U.S. government. And 40 years later, we're seeing the culmination of it take place in the form of distribution transformers of all things. And I'll specifically be speaking about immersion type distribution transformers, even though the dry type are also included in this. So we're going to really focus on what I think you guys probably see the most prevalent out there will be the oil field transformers. Real briefly, as Tim had mentioned, I work for Howard Industries. My background was mechanical and electrical side of it. I was dealing with amorphous core material back in the 80s early on with that, and so I'm familiar with amorphous core technology and a lot of the distribution, single phase pads and poles. And this is a little different when you talk about DOE, because the DOE is, of course, the Department of Energy. And the Department of, it's not, you know, some people say, well, it's the Department of Efficiency. Well, if it's the U.S. government, of course, it's not the Department of Efficiency, it's the Department of Inefficiency. So you'll see 40 years later, we're looking at what the Department of Inefficiency has come up with to help us hopefully produce a better product in the long term and the impact of it for the U.S. over that period of time. If I've got a time for questions at the end, I'm going to usually leave 4 or 5 minutes, and Tim will count me down when I get close to the end of the time period. So if you could, just write your questions down. We'll kind of hold them to the end and we'll kind of talk about them. Of course, this is a few of the topics that we're going to talk about. The objectives of this program really is to get a feel for what this impact will mean in practical terms for your organization. I'm not looking at it from a lot of theory, try to go into a lot of great detail of looking at what's the best unit for you to buy, but showing generally what kind of characteristics you can expect to see changing in the side of a transformer itself. You know, a lot of you have seen changes in your automobiles. I had a rental car coming up here. It was a new rental car where all of a sudden, you know, I thought the car had died. You go to a stoplight and you stop and the engine turns off. Well, what the deal? You know, then you hit the gas and away you go again. Well, that was part of that program, even from the 70s, to make cars more efficient, increase the fuel mileage. What the DOE has done is try to increase the efficiency of a transformer to meet higher and higher level of standards. Okay, who can tell me what an average efficiency of a transformer is right now? Anybody out there? Tim? 98%? Can I get some 99s out there? Maybe a 99 or two? Yeah. Yeah, there's some that actually are in the 99%. How many other things that you are aware of that's over 98% efficient right now? There's not very much. So this was the case where they're, you know, getting the old turnip and they're squeezing it to try to get every last bit. And as y'all are familiar with, if you've had economics, you know, there's a thing called the law of diminishing returns, which means that you try to get a little bit more, usually the cost goes up or something changes. And that's what we're going to see here is what's that impact of trying to squeeze that little bit left out of a transformer for increasing the efficiency. Briefly, we're going to hit some of the history. We'll talk about these changes, and we're going to look at also as a manufacturer of transformers, what makes it tough on us as a manufacturer of a transformer in looking at this new DOE change and how it impacts us internally having to meet this challenge coming up, and it's coming up very quickly, believe it or not, January the 1st, 2016. And also discuss some of the things that as a user, what you should look for. You know, some of the key benefits that you can see from a transformer will also be not just the increased efficiency, but you may have also weight restrictions and size limitations and all this that you'll have to, you know, that'll play a big factor into it. Briefly, I'm going to start off not in 1975, but I'm going to kind of move forward to 2007, which you saw some of the impact of that recent change we call DOE 2010. And of course that raised the efficiency standards for 70% of the transformers that were out there already. And of course, when that happened, immediately after that was done, there was some environmental advocates groups in California who sued DOE. And the suit was brought about because they didn't think the DOE had gone far enough. They should have raised the efficiency standards higher. So next thing you know, there's a lawsuit that's been filed, and as a result of that lawsuit, the DOE had to agree to an accelerated timetable of reviewing these standards and to see if they were going to be made higher. One of the things that we'll talk about is the Department of Energy set up what they call a negotiated rulemaking team, basically made up of 25 people from the industry, manufacturers, core steel suppliers, and of course they had several of the advocates for the environmental side were in this group. And I'm going to talk about that briefly in just a second. But you'll see that when they proposed a notice of proposed rulemaking in February of 2012, the intent was to have this committee look at all the available options, get the feedback, come up with a recommendation. It had to be 100% unanimous approval from this committee. Can you imagine anybody in government having 100% unanimous consensus on everything? You know, it just doesn't happen, but that's what they were asking for in this case, was they wanted this rulemaking committee to have 100% agreement on what they were going to do. And of course, the part of that agreement said they had to have a settlement on October the 1st of 2012. October 1st, 2012 came and went. November 1st, 2012 came and went. December 1st, 2012 came and went. You can see there's a trend here where the government didn't go by its own rules, but in April, of course, they actually did publish a rule. And that's what we're going to go through today, is what's the impact of that published rule that was made in April of 2012. April 2013. You'll see this is actually from the DOE actual time frame, and you can see where some of the initial work was done in 2012. It was supposed to be October of 2012, have that ruling done. It didn't really get completed and put into law really until June, because there's a 60-day grace period that they have to incorporate when they put it into law. So it really didn't become effective until around June of 2013. And then the compliance date, of course, is going to be hitting in January the 1st of 2016. That 25-member subcommittee, Howard Industries was one of the ones that was asked to attend. I think there was 3 or 4 other manufacturers of transformers, in addition to the major core steel suppliers, in addition to utilities. And so it was a good group of individuals. And of course, after meeting, I think 5, nearly 6 times in Washington, D.C., of course, that was reimbursed by the government. No, I'm just kidding. It wasn't reimbursed at all. Everyone had to fund their own way. Everyone had to pay for all the hotels. Everyone had to be there. And after all this was said and done, 23 of the members agreed we don't need to do anything right now. And there was 2 members who agreed that they should go to very high levels. They were looking at what they call a trial standard level 3, which is a very high level. Those 2 members would not go away with anything less than that. And of course, you may realize if you go back and look at the list of those 2 members of who they were, and you'll understand those were the advocates that were wanting the higher level to begin with. But what DOE did, though, right after that, was they disbanded the committee. They said, if we can't get 100% consensus, you know, this is not a democracy. We're just going to disband it, and we're going to come up with our own level that we think we should go after. And how they meant go after it meant it had to be, number one, it had to be technologically feasible, and it had to show a significant cost benefit savings without having a significant cost detriment. And of course, this was published in May of 2013, May of last year. It's actually from the Government Accounting Office, and it was kind of the summation of it. And it's about 6 pages in length. You can find it online. It's not a very difficult thing to find, but the whole focus of it was that they were putting this as formal notice that the proposed ruling had certain agreements that it was determined that the amended energy conservation standards for this equipment would result in significant conservation of energy and are technologically feasible and economically justified. So you can see, and as I mentioned, we went back 40 years, the Energy Policy and Conservation Act of 1975, how that came into play. Believe it or not, that trip down memory lane we did earlier, going back through over 40 years of looking at, and some of you are old enough, Bob, you may can remember getting in a line at a gas station and having lines of cars from the oil embargo and things that was taking place back then. But here's the result of it years later. When you look at this summary of savings, now this was provided by the government. This was nothing Howard Industries did. This was nothing like any other advocates did. This was supplied by the government based on their determination, looking specifically at the savings for immersion oil field distribution transformers. They look at it in terms of quad over a period of 30 years. So we're looking at periods of from starting in 2016 to 2045. So you're looking at a long time frame. But just to give you an idea of what they showed as significant savings for the industry. Of course, in the U.S., we're looking at greenhouse gases, reduction in carbon dioxide, nitrogen oxide, mercury, showing, and at the bottom, of course, one quad equals 10 to the 15th BTUs. Now you put this in perspective, that's a pretty big number. And then you think about that and you look at how much is that really in terms of savings annually for a country. Then you look at how much actual energy is that. And if you do some rough calculations, you can kind of determine that it's about 9.5 to 10 seconds of the energy produced by the sun. And that's over the course of 30 years. So yes, that's a lot of energy, but in the scheme when they look at it amortizing over 30 years, sometimes the payback doesn't look too good on transformers and things like that because you're really looking at longer paybacks because you're going from 98 to 99% efficiency to just 8 to 9/10% increment, but it drives the cost of the transformer up quite a bit, so their payback is not that great. And here is a, we're just putting this in there so later on when you get the presentation you can take a look at it and you can go back and review. It's great reading if you want to read it. It's got the link to the document. You can sit down and go through. It's well over 100 pages of charts, justifications. It's funny because different manufacturers, we had offered to let them use some of our simulation programs that we've developed over 40 years in the business and things like that, but they actually chose an outside group to provide some of the results and some of the things that were technologically feasible. No one was even doing it, have manufactured in that type of environment before. So it was very interesting to see some of that detail, and it has all the comments and things too that different manufacturers suggested, and really the core steel suppliers were the major influence of why this standard didn't go higher on efficiency, because there was great concern that there would not be enough core steel to supply the higher grades domestically. I tried to color code this chart. This kind of gives you an increase in efficiency. Tim had mentioned 98%. I was throwing some of the ones now, but you can look and see, Tim's right on the money if you're looking at some of these single phase items, 98, 99% as they get higher. But just take a look real closely and you'll see a difference. Right now, a 15 kVA single phase is 98.76. And typically when you look at things like that, you'll say, well, a three phase should, common sense would say, needs to be the same, because really a three phase is just three 15 kVA core coil assemblies. And sure enough, you look over there at the 45, the existing, it's 98.76. Now look what happens when they've made this change is now the 15 kVA is bumped up to 98.82. So yes, the three phase should be 98.82, right? For a 45, it's 98.92. So they actually increased, the whole focus was to look at more pad mounts, but it's going to draw in some of these three-phase pole mount transformers too. These are very, very high increases in efficiency for some of those smaller KVAs on the three-phase. And so I tried to color code them. So if you see red up there, red means that's going to be a significant change, a major impact on weight, cost, in some cases size of it. The yellow is going to be significant, but not as much. You would not expect to see as much of a cost difference or weight difference. The green is going to mean that it's going to be, I won't say minor, but in the scheme of things, there's some things you can do for tanks as far as decreasing actually the size of them, because think in terms of this. What you're actually doing is making a transformer that is less hot. You're taking watts out of it, so the thing runs cooler. It's like some of the fluorescent bulbs, when you change the incandescent, go into the higher efficiencies, where you had a 60-watt bulb, right now it's only drawing 15 watts. Well, that's what the transformer industry is doing. You're taking the heat out of it. And of course, when you take the heat out of it at 50% load, you're doing it mostly through core steel, is how you're decreasing the wattage on it. So it runs cooler, which means you don't have to have a very big tank and as much cooling and as much oil inside of it. So in some cases, it really will not be that significant of a difference, but it will be a weight increase just in nearly all cases. I use this plot. This actually came from the DOE as part of their justification, but it's a good representation. You can see, I tried to outline it so you can kind of see where they started at. The baseline was this very bottom curve, this blue curve, and if on the bottom it shows the KVA, and it's a logarithmic function. And so it starts at a 10 kVA, 100 kVA, up to 1,000 kVA. And of course they did it at a baseline, and then they went up for each standard level, one, and then they called it A, B, C, and D. Of course, was higher levels of standard. Of course, what we have now is this lower baseline. But you can see when 2016 rolls around, what they do went to the TSL level 1. And that gap right here above 100 kVA is where you're going to see a major shift in the size and weight of units. So so it kind of shows you it took a big jump in that particular area of the efficiency levels. Now, practically, what does that mean? Some of you may have had concerns over the weight of some of the pole-mounted units, and of course, when the DOE was looking at it, they actually did consider that, because they heard so many complaints saying, if you got to go up one more size of, if you increase the weight of these poles any significant amount, we're going to have to increase the pole size, do pole changeovers. It'll be pretty tough to do. So what they tried to do is to impact most of the pad-mounted equipment. So the pads, they were thinking, well, it's going to be on a concrete pad or some type of a pedestal-mounted pad, and they didn't realize that there's size and weight constrictions even on those. But you'll see how the weight increased on some of these pole mounts also. I started off at 50. We probably could have started off a little bit less. Some of the ones didn't make a big impact, but a lot of times, if you can hang a 25 kVA, then the concern or that crossover point is around that 50 kVA line, because the weight goes up quite a bit. But you can see the major increase in the 50s was the core coil assembly weight. We actually went down on oil. And you'll see the cost impact was very insignificant. So you can see there's some things that make a little sense, because when you run more efficiently, you can put more core steel in it. You can actually try to decrease the size of the tank. You won't need as much oil in it, so without as much oil in it, it drops the weight. Of course, core steel is going to be, if you're looking at the price of a core steel versus oil, transformer oil is probably in the neighborhood of 50-some cents a pound. Core steel is going to be, well over that. It would be about $2+ a pound for that. So there's a trade-off cost that takes place. You can still drop oil, but it doesn't overcome the cost of the core steel. And of course, when I looked at this information, I was basing it on current market conditions. And we all know how that changes so much. The big concern is that what's going to happen to this impact is not just the immersion transformers, it's the dry type too. The dry type is going to start using up some of the core steel. the higher grades in order, because their efficiencies are going up too, so it's going to be a limited supply of the better grades of core steel, the M3 and M2, and I'll talk about those in just a few minutes. Single phase pads. That's always my specialty, because that was always one of my favorites, was single phase pads. I always liked single phase pads for some reason. And the previous company I worked for, we used what we call a top load design, which actually put the core coil assembly through the top of the tank, weld the cover on it. And that works good, but you got to realize when you have the larger the core coil assembly, the bigger tank you have to have, because it has to go out and you have to be able to squeeze it in there. Howard uses a backload design, which is a little different in that you actually will invert the tank, put the core coil assembly in through the back of it, which is a lot bigger opening, and weld the back up. So you can fit a lot larger core coil assembly inside the back of the tank without impacting tank size. I had to preface that because some of the numbers you see, it really doesn't change a lot on the size and weight. And other manufacturers, you may see other differences in this because they're going to have to go to a larger tank, more oil, more weight impact. So this kind of gives a little bit of a difference of what we're going to see on the single phase pads. You're going to see somewhat of an increase in that, but depending on, you have to see how the unit is built, whether it's a top load or a back load design. Top loads, you're going to probably see more of an impact. Back loads, you'll probably see less of an impact. Three-phase pads, you're going to see a significant increase in certain KVA sizes. There's just no doubt about it. All of those go through the top. You can't do a back load design. You always have to put them in through the top side of it. So you're going to see increases that'll, in some cases, I'll show in 28% increase in the weight of the core coil assembly on some of the larger KVA sizes. You got to think in terms of now, a lot of the smaller KVA sizes, you can actually, the core coil assembly or the engine for it is a very small part of the bay of that tank size. So you actually have a lot of oil, a lot of what I call oil space inside of it. As your unit gets bigger, of course, your core coil assembly gets a lot larger, that oil space gets consumed. So what we are seeing, though, is kind of unique, is that we're trying to keep, by keeping the size of the tank down, which you can do because the overall heat is less for some of the three-phase, it still nevertheless increases the weight of them, in some cases, very considerably. You're looking at the weight of this one, in particular, is 500 kVA, going up 14%. And I'll show you some of the actual numbers on that too, so you'll get a feel for it. And I put up just a chart of comparisons. This was a design that I'd looked at some existing designs for some customers up in the Northeast, trying to get a feel for what they would see as far as the change. And you can get a feel for that when you look at the efficiency level going up. It's not, this is not 99.08 to 99.11. We're not talking about a major increase, but you can certainly see that the impact of it, it actually drove down the amount of oil from 18.7 to 14.4, but look at the core coil assembly weight. And so that tells me, and I couldn't get the physical dimensions on this one, I apologize for that, but you can see where the total weight actually goes down in this particular case. Why? Because the tank size actually went smaller. So when the tank size went smaller, we're actually able to put it in, use less oil, just less displacement on it, so you actually fit in a smaller tank. And notice that the winding rise, the temperature winding rise, 65 degrees C, it's pretty close to the ANSI max on the design of it. Now that's important because you'll start to see some pretty low numbers here in just a few minutes. When you look at it, it's good and bad. It's, there's been talk about, can we run higher thermals with, a lot of you familiar with FR3, the seed-based fluid, and great product, and yes, it runs hot, but the problem you run into is that these units run so cool, it's hard to get them to that level of winding rise on it because you have to have the tank, your tank size is your limitation. So right now, some of the designs we're looking at on pole mounts where FR3 material looks good at 50 kVA for possibly, extending the life, getting very cost-effective life out of it versus the weight of it. Now you're talking about a unit that's going to be even more efficient, so it's going to make your fluid requirements less. So you're probably looking at 75 or 100 kVA before you start seeing any kind of benefit with FR3. You know, it's going to be a lot higher kVA size. Because we try to look at some where it was 10, 15, 25 kVAs, and you really couldn't justify it because you're only running about 40 degrees C rise on it. You never could get it up high enough. 100 kVA pole mount, I want to touch base on that one real quickly too, because you can see that's only 0.2% difference on it, but yet it still made a fairly significant impact on the core coil assembly size of it, and with the similar winding rise, so you'll see a little bit larger increase in weight. You're going over 1,000 pounds with these things with 100 kVA. And I flipped over to the 50 kVA pad because this one, you know, some of these are very, very unusual. When you look at the winding rise on this one in particular, you can see that we're nowhere near 65 degrees C winding rise on it. With the amount of oil in it, with the size of the core coil assembly in it, it just runs really cool. And of course, when 2016 impacts it, what's going to happen? It's going to run even cooler. You know, it's going to look even a little bit more oil in the size of it. This one actually went down too, because that was one of the ones that this particular customer, you know, when you run the analysis, you kind of get a feel for how many people are already meeting the new requirements. And in this particular case, even though this customer didn't have a formula, they were actually meeting the 2016 requirements off of it. So you can see that it was the core coil assembly weight actually went down slightly. But here's another one on the 75 kVA. I'm going to flip through these pretty quick because this one is also a situation where you're going to see the weight of it increase 15%, which will impact the cost of it. And we're trying to keep the size down too. But you can see just generally these units are going to be way more. Core coil assembly is going to be heavier. The core coil assembly is the engine. That's the cost of a unit. You know, typically it runs 70, 80% of the cost of the unit is just the core coil assembly. I flipped over to the three-phase pad just to kind of give you a feel for a few of those dimensions on it. When you start looking at a three-phase pad in particular, because of these slight increases, you're seeing a fairly significant amount of increase in the size and weight of the unit. But notice again the winding rise. The current design was running at 65 and it was re-optimized and to the 2016 running 46 degrees C, which does mean, yes, you got a little bit of room to overload it off of that. So it does, I mean, you got basically a V8 engine in the repertoire where you used to have a V6 before, so you got more power, that's usable.
I got a question here. So the DOE efficiencies were based at 50% loading. So if you had this flexibility with increased winding temperature, many utilities would look to exploit that, in which case don't you subvert the benefits that were gained by increasing those efficiencies?
Yeah, that's a great question. The question was, looking at, the standard was based on 50% load. So how can we maybe use that to our advantage when we're looking at system design to see, where we're using a 50 kVA before, now you've got, basically a unit that's going to have close to a 60 or 75% or 75 kVA capacity in it. And we are seeing a lot of people look at that. And I'll show you a few diagrams on that too, because I think I've got a couple of things you can look at for tools to go by. When you're thinking about doing something like that, there's a lot of utilities thinking in that term is, we got extra core coil assembly, weight, material, adds to the kVA capacity of it. And this ties in with just what you said. It was on the next slide. But if you look at that, the no-load losses were based on that 50% load requirement. And of course, that means you're going to have more core steel. has anyone ever seen a core being formed before? We got a few people. We got a couple. Okay. I'm going to kind of describe it as best I can. If you can imagine most of this core steel material, if it's silicon grain-oriented core steel, it comes off of a reel, and the reel is usually what they call a strip width. Most of the material that we're going to be talking about here is going to be about 7/1000ths of an inch thick. It's probably not much bigger than a business card thick, sometimes a lot thinner than that. As it's de-reeled off, it will actually run through a machine called a Tranco. The Tranco will actually measure the length of the loop and then cut it, and it's staggered every cut. Now imagine when you have to go to thinner material, but you've got to have more of it, and you can't increase the speed of your Trancos. That stays constant. So what happens is, you know, if you have more length you got to run out, more cuts you got to make in between each layer, more material in it, it takes longer to actually wind and cut these cores. So manufacturers will be facing this issue of capacity, because now you're going to be running thinner core steel stock through systems on it, which is going to impact capacity, but will give you an extra capacity out in the field because of the extra no load side of it. How many of your systems out there run less than 50% load on your transformers? Anybody got a feel? Yeah, most. Are some of yours over 50%? Yeah, I think, and I'm going to show you a slide here that'll at least get you thinking in terms of, you know, let's take a look and see where the loading is on these transformers, because I know it's very cyclical and things like that too, but there's ways you can take a look at it and make sure that you're buying and using and designing the right size of transformer for your application. Real briefly, the conductor loss is at 50% load. Of course, that means that, you know, if you're looking at that, that's 25% of the losses typically, rather than 100% load loss. And this was that slide I'd kind of alluded to before on the different grades of core steel. This is looking at silicon core steel. This grain-oriented core steel that, you know, it's designed to be very low loss. It's designed to be, you have to anneal it after you form it. So it's you know, it's not your typical tank steel or any kind of production steel like that. And there's only, you know, domestically there's AK and Allegheny are the two domestic suppliers of it. And then for amorphous material, it's going to be Metglass are the two. But you'll see right now we've actually got some designs that are still using M4. M4 core steel is about 9/1000ths thick. It's a little thicker material, and it's and there's an abundance of it. And there's quite an abundance of M3. Where you run into problems is that if you have to see a major shift going to M2, I'm sorry, it's 9 mils, 7 mils thick on the M2. Now amorphous is completely different. Where silicon grain-oriented core steel is actually rolled through the mill, it uses rolls on both sides and flattened out. The amorphous is actually poured. It's actually glass material that's poured over rolls on it, and as it's de-reeled out, it makes nice strips of it. There's only several different widths of strips that you can get, and it's only 1 mil thick. Just imagine taking some of your, do you have aluminum foil at your house? Everybody's got aluminum foil? Just pull out your aluminum foil. That's about 4 mils thick in most cases, 3 or 4 mils thick. Imagine 1/3 of the thickness of that, and that's about how brittle it is. You know, you can tear it and twist it, but electrically, it has hardly any resistance whatsoever. Excellent magnetic properties. And I'll briefly touch base with some of that because you can kind of judge, you know, we're starting to see more of the amorphous. For us as a manufacturer, we're close to 20% of our production's amorphous capacity now, so it's changed quite a bit. We made probably 500,000 units during the 90s and early 2000s for amorphous core, and then it kind of shifted away because they tried to raise the price on amorphous core. And then when the efficiency levels came back in, we actually unballed the equipment, took it out, started using it again, and actually had quadrupled the size of that production capacity because it's been so active. but it's a significant investment. A lot of the manufacturers didn't want to spend $20 million to buy the amorphous equipment to set it up and run it. And if you haven't run it before, it is a learning curve to get in operation. One of the biggest things is everyone looks at what they call the stack factor. On a silicon steel, you're looking at flux density of the core, and you're looking at how one layer stacks on top of another. And for silicon steel, you can see it's right at 0.95%. So when you stack it up layer by layer, it's 0.05 of an air gap between them, or a slight gap. If you look at amorphous steel, because you don't roll it on both sides, it's only flat on one side, it's a slightly less, there's more air gap between it. But when you're talking about the super efficiency of the amorphous versus the highest grade of M2, the amorphous wins hands down. It's just very, very efficient. The only good news, there is one domestic supplier, maybe not good news there, but the other side of the good news is the patent for it is expired several years ago. So before we couldn't even get it in the quantities that we were looking for because of the most of us being exported, going over to India and China, but because of the patent's expired on it, a lot of it now is going domestically. Real quickly, I put this up there using the 2010 DOE. Now take a look at these areas under the curve. And for you engineering types out there, the guys that go in and look at your mileage of your car and make notes on it, here's a good rule of thumb right here is you're always looking at trying to track the area under the curve. The more area under the curve, the better your transformer is. And a lot more practical. You can see where this one on amorphous, it starts above the efficiency level required by DOE. It actually goes above that and then tapers off above 50% load. It starts to taper downward. Now take a look at this one, and this is a silicon core steel design. Notice the different characteristics of it. You'll see it starts at a lower efficiency, actually ramps up to the 50% load, and then ramps down. Now when DOE first came out, there was some gray areas of it, and some manufacturers took it upon themselves to say the only area I have to be concerned about is this 50% load. And so you can actually design a transformer to start off way down here and kind of ramp up and then ramp back down very quickly. And that's a very narrow window. And of course what happens is you don't put as much core steel in it. Your core saturates, your losses go up higher. So there was some things that people were doing, and all of a sudden their newer DOE designs were significantly less in weight and cost, and in a lot of cases that was what was happening was that, yes, it ran 50% load and it was right on that DOE efficiency where it should be, but within that range, that area under the curve was very small. And so we see units starting to burn up where they hadn't burned up before, and they shouldn't have burned up because they were trying to hold it to a narrow bandwidth. But when you look at the area under the curve, that's the key thing. And most manufacturers can supply that. If you look at certain designs, just have them look at 25, 50, 75, 100% load, and also have them look at 110% overvoltage. That way when you look at overvoltage, it'll tell you how much if your loss watts starts to jump 30, 40, 50%, you know that you don't have as much material in it. You shouldn't see that much of a shift on it. But one difference I wanted to point out though between the amorphous, because the amorphous at that 50% load, it starts to taper off. Of course that allows you to put the amorphous cores are actually larger, but the coil becomes smaller. So there's a trade-off on it. So if you run over 50% load, guess what? I'd probably tend to go with more of the silicon type designs than the amorphous. Because the amorphous will tend to, it's more backloaded. Usually it's going to be more backloaded on the winding side than of the conductor rather than the core side. If you're looking at purchasing transformers, got any buyers in here or that recommend to buy? Not too many? well, y'all probably don't care about this, but you can go stump your purchasing agent the next time you see them, because they may be asking you for this, is look at for A and B factors. You know, that's kind of been a rule of thumb as to, you know, if you know your A and B factors on it, and of course that indicates your no load and your load loss characteristics, it allows manufacturers to actually design an optimal design of a transformer for your operation. And that'll tend to, I won't say skew, but it'll certainly change the design enough so it'll give you exactly what you're looking for. One good example of this, and you're going to see it here recently in 2010 DOE, the current method of operation, when you look at about $3 and $1 on a three-phase pad, then you start seeing the possible need to maybe consider amorphous. Now you're going to see that crossover point shift. It's going to go up a little higher. I think it's going to, you know, from what we can see, it's going to be about a $4 and a $1 for the single phase, and it's going to be over $5 for three phase, $5 and $1 for three phase. So you'll see that little bit of a shift between the single phase and the three phase between your A and B factors. And as the last line mentions down here, you know, most of these total owning costs, they actually look at that ratio, that core conductor ratio on it, and when you optimize that ratio for your operation, then you're assured you're getting the best bang for your buck. Real quickly, here's a quick slide that we try to put in for it, showing if you have two different units, you got design A, design B, both of them meet the efficiency level. There's difference in the core material between both of them and the conductor between both of them. But you can see that the total owning cost for design B is actually higher than the design A, even though both of them meet the efficiency level. And you can see one of the reasons why is that, you know, the cost of the core and the conductor on this one's got more material in the core side of it, which keeps the cost down. This one has less material on the core side. But you can see how the total owning cost, of course, is impacted by the ratio of that core and conductor. Just be thinking about this if you're looking at designing and changing over for DOE 2016. I can give you our numbers on it approximately of what we're looking to do. About 7,500 different active catalog numbers have to be redesigned in the next, really about the next year, about 12 to 13 months from now. So there's a lot of rework that's having to take place, redesign, re-optimizations of it. Most manufacturers will have to start ramping down and ramping up. You'll start ramping down on the old designs toward the end of the third quarter of 2015 to start ramping up for the new designs. After January the 1st, 2016, we cannot sell any units after that point that, or they can't be imported either, that do not meet the DOE 2016 efficiency standards. They can't be built. There are some customers that will, you know, as long as we can build it before then, the old design, we had quite a few of those during 2010 where we built 5 years worth of certain items that they knew that they couldn't get them the new way in the size they wanted, so they got 5 years worth of the old design. And that carried them over, you know, until we give them a chance to redo vaults and things like that to make it fit, make everything fit. One of the things I wanted to mention quickly on it was during this DOE period when they were doing some investigations of going to different facilities, asking questions, trying to get all the data together for the presentation of what they would present to the DOE and make their suggestions. To give you a flavor for what they were doing, we had a group called Navigant, which is a pretty big consulting group, came into our facility, spent about 4 days with us going through the plant, and I'm showing them through tours and we're taking them through the different areas, and it was very interesting. They didn't say a lot. They were taking notes and writing things down, and I finally understood why they didn't say a lot. We got over there to the area of the single phase pads, you know, that's the area I like to go to, and had a transformer with oil in it, you know, because these are oil filled transformers, and one of their consultants came up to me and And they were as serious as a heart attack, as they say in the South. They go, you know, what do you do with that oil? Where do you pump it out when you're, before you ship these things out? I went like, pardon me? And he says, well, you know, where are you dumping this oil out? Don't you reuse this oil? And no, sir, it stays with the transformer. You know, these are oil immersed transformers. Okay. I'm going like, oh my gosh, these are the people making the decisions, and they really had no clue even how a transformer was made. I mean, I could have showed them the green box, and they were like, well, yep, that's a transformer, but they had absolutely no clue, and they're the ones going back to the government. But I could see why they didn't say very much, you know, because they didn't want to open their mouth, and they didn't say ask any more questions after that either. but it was interesting, you know, because these are supposed to be the experts, going back to the people that know to present the details. So that's what you're dealing with. You know, sometimes it was just kind of ironic. But real quickly, I just want to conclude with this. We got a few minutes here too, and I'll take some questions. You know, look at these transformer numbers in a little detail, and you'll see that yes, they are increasing. Some of them are increasing significantly. When you look at the core prices and the costs that'll be impacted, I don't think we have a firm, I don't think anybody has a firm contract number yet of what that's going to be in 2016. But I would expect to see increases in the core steel price because it's going to be a supply and demand issue. There's going to be a lot more of a need for M3 and higher grades, and I think the amorphous will keep it competitive, where hopefully there won't be a large surge in housing starts. It would be nice to see some increase, but not like we had it in 2005 or 6, where it was just through the roof housing starts. That would cause a lot of problems. But they are going to be heavier. You can expect the weights on some of the 3 phases to be significant on some of the larger KVA sizes. And we also suggest, you know, using your A and B factors. You know, if you haven't done that in a while, get them updated so you can evaluate, see where your transformers run efficiency-wise on it, and then you know, and then kind of know what you're buying. You know, when you look at it, one of the best buyers I ever run across one time, he says, now what am I buying when I run into a transformer? And he says, you know, is it and the only thing he knew was, is it a gray box or is it a green box? A gray pot or a green box? You know, and that's all he knew. I said, well, you know, what you're looking for actually is not what's on the outside of it, it's what's on the inside of it. So you look for your core coil weights, and you look for, you know, your efficiency, your losses on it. And that's always a good check, because then you know what you're buying, and you're getting, you know, you're checking under the hood is what I call it. You know, you're looking under the hood and see what kind of engine is that, and you know, you kind of know what you're buying. I had a few minutes here for questions on it. Any other? Yes, Tim.
At what point is it going to be where silicone steel is not even practical?
Boy, you are. Yeah, there's going to be, you know, in 10 years, I think we'll see a shift in how transformers are. You know, I think you're still going to have the silicon grade, silicon type units. I think you'll see more amorphous come into play. I think you may see some of the solid state transformers start to grab hold a little bit in certain applications. That's something that's fairly new. Real briefly, you know, we've been working on what we call a solid state through EPRI for 5 or 6 years now, and that's something that's going to, right now it's still developmental, but it's modular. You can actually, and we're not really calling it a transformer because then it would apply to some of these rules that it doesn't need to apply to. So we're actually, we've got some beta sites in test now that we're working on. So it's going to be a difference. I still think you're going to see silicon, you know, probably for the next 15 years though, in some fashion or form. It's $1 billion for the manufacturers to build a new silicon core steel manufacturing facility. $1 billion. And that is a pretty small niche in their marketplace. But to get to the higher levels of core steel, gee, I can remember when I first started in the 80s, we could get M1. We could get M1 grade core steel, which is a highly efficient core steel. But then everyone was driven more by price than by actually what you were getting for the losses. So most of them converted and started running volume out rather than the quality. So they started going to M4, M5, M6, and now it's going back down again. It's going M4, M3, M2. So we'll see a major change, major shift.
So do you think M1 will show up again?
It wouldn't surprise Mark if M1 is the what was always called the ultimate core steel gauge. It's I think it's maybe a thousandths difference than M2, but the efficiency level is about 15% higher. So it's right now it's the only way we get it is that you'll see it on a core of on a reel of M2. Now you have to think in terms of this. If you haven't seen this stuff being dereeled, but when you're looking at core steel, it's not uniform throughout the entire reel. They'll actually sample the core steel as it's dereeling. As you take samples, you'll see, this is M2, this is a high M2, this is low M2, this is just on the verge of M3. It's not uniform when you dereel it. What we have to do as a manufacturer, we'll actually get every core and we'll actually test it for losses on it. And we grade it basically. We give it an A, a B, or C, or an F. I don't think anybody here ever got Fs in school, did they? No. These are all A's and B students here, I can tell. But you can see that that's a big part of it because we have to match them up. And when you match it up so that you try to get if you got a C, you want to put an A with it. You got a B, you want another B with it. You try to have it so it's at least an A or a B. And that way, when you get all your transformers in, and there's a technique we call loss banking. Loss banking is basically saying, let's say that Howard Industries quotes transformers to Tim. Tim says, I'm buying these transformers, here's the quoted losses. We send those units to them, we provide certified test reports, but we also do this thing called loss banking, and that way we actually accumulate the actual tested values of the core and the conductor for all those units. And if they fall underneath that quoted amount, that's energy dollars that you're saving, because that's dollars you won't be paying out extra. And so we see customers start looking at that and actually looking at that as part of their value in a transformer, is banking those losses, because that's something that you can do as a user, that you can show your boss to say, hey, we're actually getting a pretty good deal for our buck here, is that these units are coming in, the losses are actually under what was quoted, so we're actually saving dollars on it. But yeah, that was a good question, Tim, is what's the impact of silicon steel going to be, and is M1 going to be available? I doubt if M1 is going to be much available, but I think we're going to see them start to look at spending money, but it's about 4 years to get that $1 billion plant up and going too. And they're not rushing out to lay down brick and mortar right now, I can tell you that. They've got a pretty captive market. I think we will see more impact of international core steel, but there's some issues going on right now, because in about 2 months, there was some dumping that took place a couple of years ago, where overseas manufacturers were dumping core steel in the U.S. marketplace, and that's going to have an impact. It certainly will. Yes, Bob.
Well, Ken, what's the impact, since the laminations are thinner on the core, what's the impact of faults affecting the core, since it's a thinner lamination?
Yeah, and Bob, we haven't seen too much of that. And the question was, when you're looking at the thinner gauge material, especially on ground faults, what's going to be the impact of thinner gauge core steel during a ground fault situation on it? And a lot of it is because of we're talking about that gap on it, is that if you have a 7 mil material and you've got a 0.05% air gap, and now these cores are getting larger and larger, and you potentially of having a lot higher fault current going through it, and more bowing out. I would expect you're going to see some increase in that just from the, typically the core clamp's going to take care of most all that, but it is going to be a lot heavier. So what we're doing is having to beef them up. When they get a certain size, they actually have to be beefed up and go outward a little bit and make them a lot stronger. Hope that answers. Any other questions? Well, I appreciate you very much for your time and staying awake too. Is after lunch, and I know that's difficult to do. Thank you very much. I appreciate it. Thank you.